provide straightforward content. I fully expect that those who listen will come away with a technology that's value added. There are 2 slides devoted to who's METSS. There are 4 slides that describe the technology, background, sort of the why behind METSS's pavement repair technology. The technology was developed under a Small Business Innovative Research SBIR project. The contract on the agenda is shown. The requirements and specifications are explained kind of as a prelude to the testing and evaluations. I have 6 slides that highlight the field demonstrations, and then I conclude with 1 slide that offers applications and benefits. So thanks again for allowing me the time to explain who we are, what we did, and why it's important. So on slide 3, METSS Corporation. METSS is an acronym for Materials Engineering Technical Support Services. This company started 30 years ago, 1994. We see ourselves as an applied research firm. We offer practical solutions for government and industrial partners. However, the majority of our work is sponsored by the Defense SBIR program. Our intent is to perform research and development with commercialization as the end state. In other words, METSS does not perform R&D purely as a theoretical exercise. Technologies that we developed are considered successful when they can be transitioned to an end user, whether that's in the defense world or in the non-defense applications. On slide 4, we have several core capabilities. Our fluids work, for example, included a U.S. Navy contract set out to design a synthetic oil to replace the mineral-based oil used aboard nuclear ships and submarines. The existing product used aboard ships and subs, it's been around for about 80 years. It's called 2190 TEP. It stands for turbine extreme pressure. So against several challenges, METSS created a synthetic counterpart that's 100% compatible at any ratio up to a full synthetic system. Success was realized after extensive design and qualification process. It lasted nearly 12 years. And that success was certainly a credit to strong support by the Naval Sea Systems Command, NAVSEA. Today, METSS is the sole provider of the 2190S or 2190 synthetic, which is being adopted by Los Angeles-class submarines. 1 Virginia-class submarine has it fully adopted the METSS synthetic oil. Other classes of submarines are slowly moving toward that technology. METSS is cited by name in the military specification, the MIL Detail 32353A. Their most recent revision of the MIL spec was published in February of 2021. The demand signal, as of 2014 has continued to increase. So we're in a good position to continue to support the Navy in that capacity. We've been involved in a number of projects related to advanced chemistries as well, mostly in the world of depainting operations. For example, we developed a solution to replace methylene chloride. This compound is used ubiquitously throughout the military to remove paints and primers, especially on aircraft landing gear. Despite being incredibly harmful to human health, methylene chloride is a neurotoxin. Another example shown here is a technology that METSS developed to remove powder coatings from soft metal components, again, aircraft or Air Force supported. We developed this technology to replace a high pressure water process that worked effectively to remove the powder coating, but in the process of removing the powder coating, it was destroying all the parts, or most of the parts. The attrition rate was incredible. Another core area includes lightweight fuel systems. For years, METSS has been working with the military and prime contractors to develop lightweight fuel bladders that self-seal against significant ballistic events, as well as crash. This work has been applied to U.S. Army helicopters as well as U.S. Marine Corps combat vehicles. as you can see in the picture. So like many of the project METSS has continued to be involved with, the pace of integration depends largely on the end user support and willingness to modernize. So, here's why we're here. These next few slides are going to explain the why behind pavement repair. So in response to a 2016 SBIR announcement about rapid runway repair, this project began to take shape. The problem the Air Force was facing was obvious. Air Force runways were being bombed. Mission profiles were being impacted sharply. So at the time, the Air Force was using these large, cumbersome mats to mitigate against flight takeoffs and landing downtime. These mats were considered temporary, so the Air Force was looking for more of a permanent solution. So continuing on, not surprisingly, airstrips are vulnerable to munition attacks. The requirements, the specification for an effective runway repair included the following. The patch formulation, it needed to be simple in terms of the components, how they would be mixed, how they would be poured. Equipment cleanup should be easy, limited to like pressure washer using water. The cure cycle, meaning when the patch is fully gone through its process to solidify, had to be under 60 minutes from the time of mixing. The upper limit was 2 hours maximum. The post-cure patch must be strong enough to sustain load forces that exhibited by the transport and fighter aircraft that you see in the presentation. The precise specification was 1,700 psi. Another key requirement was the patch had to be applied in all conditions, to include rain. The technical challenges against these requirements included a streamlined process for screening materials. METSS technology was based on an epoxy, which was called our Part A. Part B was an amine, which was a curing agent or a curing promoter. And Part C was just a local aggregate. But optimizing these ratios between parts A, B, and C, that was one of the significant challenges, because this is largely due to the ambient conditions, including rainfall. Going back, it's also important to note that the cavity, the hole that we were going to fix, or patch, if you will, was going to have to include, fragments from the blast. So, it was going to have to be reinserted along with perhaps a utility one fill or a sand to reduce the free space within the cavity. So Key was designing this 3-part system to cure fast, sustain high load bearing forces, and also bond well with the surrounding surfaces. For the purposes of this work, the cavity had to be squared off, or was squared off. So it had well-defined edges to demonstrate performance. The repair solution had to be able to be safely stored. So a long shelf life. It also had to be transportable. So getting it to where it needed to be overseas was important. Repair patches must be affordable. Cost is always a factor. This is especially true when you're trying to penetrate industrial markets. In terms of the approach, we saw this as a formulations development opportunity, really, to use commercially available products that could be tailored into a system of chemistries to achieve the objectives. So screening the materials required a concerted test and evaluation system. The primary lessons learned were the ratios between parts A, B, and C. And they really drove the cure cycle, and they depend heavily, I can't say that enough, they depend heavily on the ambient conditions, meaning the temperature, rainfall, etc. Accommodating rainfall, again, was a significant challenge given the heat generated, and then using that heat to displace pooled water within the cavity. Trade-offs exist between the load-bearing strength and the cure cycles, both of which are byproducts of, again, those ratios. So I just mentioned the lessons learned, but what's shown is two perspectives of the mixers that we use. We bring those to the site. They're a quick spray carousel mixers. They're easy to clean. They use easily cleaned by water. We use the static mixer transfer lines. You can see through these PVC lines, so you can watch the material as it mixes and goes to the cavity itself. So, this was a big R&D effort. Where the rubber meets the road, so to speak, is when you can take what you've learned in the laboratory and do that out in the field. So these next 6 slides are devoted to demonstration testing. So for this first field trial, we traveled up to Minot Air Force Base in North Dakota in February of 2019. The ambient temperature in North Dakota in February was 6 degrees Fahrenheit. The cavity that we sought out to demonstrate repair, was 4 square feet, 4 inches deep. Temperature of the surrounding concrete was -7 degrees Fahrenheit. We poured 810 pounds of epoxy-based patch into the cavity. The mixing, the pouring, went as planned. There was sufficient time to work and level the material, as shown in the photographs. By all counts, everything looked good. Even the cure cycle was within the objective limit, was less than 60 minutes. However, there was, and you can see by the IR camera, a significant, substantial thermal gradient on the patch itself, when looking through the IR camera. The cold ambient temperature caused the edges of the patch essentially to contract. It pulled back, as you can see in the rightmost photographs. So during the load cart testing, when they take the cart that's weighted down to produce the 1700 psi, the patch rocked. It showed evidence that there was some cracking going on. So this was a big lessons learned. I point this out because not all research comes out of the gate, with glaring success. But what we learned is that we need to adjust these ratios to accommodate these cold ambient temperatures. So the next demonstration we did took place at Tyndall Air Force Base down in Florida in July, roughly 4 or 5 months later in July 2019. The most obvious difference was from the last test was the ambient temperature. The outside temperature in Florida at the time was 88 degrees Fahrenheit. The cavity was increased from 4 square feet to 8 square feet. The amount of material we used increased from 810 pounds to 4,000 pounds. However, the biggest unanticipated event during the trial was that it started to rain about 20 minutes after we started loading the mixer. This caused the patch to cure much faster than what was otherwise expected, which decreased the amount of time we had to work the patch, meaning to spread it out, to level it, and so forth, even though it is self-leveling. In short, the rain deactivated the cure cycle, which caused the patch to exhibit a poor adhesion to the surrounding concrete. Cracks occurred during the load cart testing, so more lessons learned. So in a nutshell, Minot Air Force Base, that exposed cold temperatures. Testing at Tyndall prompted METSS to consider the rain component. How do we develop formulation, a patch that can, withstand rain. That was a big driver for continuing on. So in the next slide, more demonstration testing, same year, this time fast forwarding to October. We went to a National Guard station in Indiana. Temperatures, ironically, were identical to that in Florida, 88 degrees Fahrenheit. We reduced the cavity size back to 4 square feet. Again, we used 800 pounds of material. So without rain, without any of the other extreme temperatures, the patch cured well within 60 minutes. So this was considered a win. The work time was 40 minutes. Again, the patch behaved, as expected. There were no signs of cracking. The heavy equipment that drove over the patch, post-cure, post 60 minutes, had no visible signs of degradation. So, all went well. So yeah, we came out of this demonstration with some positive, with a definitely a positive feeling. In this slide, this was our final field demonstration. It took place in June of 2022, back at Tyndall Air Force Base in Florida. For this trial, METSS was tasked with filling 2 cavities. One was 8.5 foot squared, and the other one was 4 foot squared. The one thing about the smaller hole, the 4 foot squared, was that METSS would be conducting this repair under a simulated rain system. So they had this large canopy that came over that essentially sprayed water on the folks that carried out the repair patch. The 8.5 foot was outside. It was bright sunny day. We poured 3,300 pounds of material into the patch. The mixing and the pour went as planned. Again, like I said, we had tailored the formulation with the trade-off that the cure time was going to be a little bit longer. So this one took 2 hours to cure. But there was plenty of time to work it, plenty of time to spread the material throughout the cavity. If I didn't mention, it was 86 degrees Fahrenheit at the time. During the load cart testing, as you can see in the presentation, there was no evidence of cracking. The patch didn't rock. Again, the reason the cure time moved from 60 minutes to 120 minutes was that METSS had to create this formulation that could handle cold, heat, and rain. So in other words, we had to develop this formulation at a minimum to repair distressed surfaces in warmer climates during rainfall. The Air Force decided that cold temperatures were important, but not as important as rainfall and higher than ambient temperatures. Continuing on. So the smaller patch worked great. We had tailored this patch to work in the rain. Again, it was a 4 foot square hole. The cavity was filled full of water before the patch was inserted into the cavity. When we did do the pour, the water was quickly displaced. For this particular cavity, 570 pounds of material went into the hole. Load cart testing was carried out. Again, there was no evidence of cracking, no evidence of the patch moving. So by all accounts, the demonstration testing at Tyndall, was a resounding success. The primary takeaways, what we found out was that we had a formulation that had a strong adhesion to the surrounding concrete. The patch exhibited exceptional load and compression strength, upwards of 4,000 psi, more than double what the objective 1,700 psi had called for. You can see the landing gear of a fighter that exerts this type of pressure. So also note is the coefficient of friction being greater than 0.5, just as a side note. So so in conclusion, METSS technology has a broad range of applications. We stand by this product. We think it would be ideal for shipyard repairs, meaning dry docks, pollards, mooring cleats, anything that requires strength in terms of the tie down points. Roadways could be a huge benefit, or could benefit. Parking lots, garages, any distressed surfaces. Bridges, that's been brought up a number of times, that either the superstructure, the substructure, or the substructure pier could benefit from this technology. Basically, any paved surface near salt water that's subject to a wide-ranging temperature could benefit. This technology could be form casted. You could make footers, jersey barriers, blast walls, curbs. The benefits, they're far-reaching. The technology could address concrete-related cracks, spalls. It could be used as a facade, essentially to help all repairs in terms of any debonded materials. Also worth noting is the repair patch produces no toxic gases. As I mentioned, it's self-leveling. It's a 3-part system, as I've mentioned. It works especially well at room temperatures and high temperatures, and obviously works really well, during rainfall. METSS considers this patch a forever material, meaning the surrounding material is going to degrade faster than the patch itself. So with that, I hope that this was educational. I appreciate your time, and I look forward to the questions. Thank you very much.
Thank you for joining Liftoff Webinars, where we propel American manufacturing into the future. Stay tuned for more informative webinars that have the power to shape tomorrow's manufacturing landscape. Discover more about LIFT, our groundbreaking projects, and membership opportunities at lift.technology.
So Brian, thanks for that great presentation. Appreciate your expertise. And there was we have some questions coming in. Obviously, you learned a lot in these testing and verification, formulations, where it applies in shipyards, roadways, bridges. Let's get started with some questions. Are you okay to take it away with some questions, Brian?
Yeah, absolutely. I appreciate everybody for coming out and listening to the webinar. Very cool.
Excellent. So I'm going to start off. So in terms of the fully cured repair, how fast can traffic resume? And did traffic resume when you were at Tyndall? Did traffic resume both, I guess, in Florida and Indiana, because you tested in both of those? So how fast can traffic resume?
So the short answer is roughly 2 hours. You pour the patch, 60 minutes later, it's good. An hour after that, so 2 hours total, the patch is good to go. So if this were used on a roadway, for example, a couple hours, you could have resumed traffic.
That's significant. And the fact that it's a forever material, and obviously, as you are talking to the ecosystem of the National Advanced Material Manufacturing Innovation Institute, I'm sure everybody is keen on learning what you've discovered along the way. So appreciate you sharing. So another question that has come in: how are you marketing the product to FMS customers for uses that you've already mentioned? And FMS, for those that don't know, is foreign military sales, or is this product maybe ITAR controlled? Can you talk about that, Brian?
Now, whether or not it's ITAR controlled, I'd have to take a look at that and get back to the person who's asking that question. I don't think it is, but to get to the question, how are we marketing? In truth, we're going to conferences. This was a big marketing opportunity, quite frankly. Anytime we can get in front of people who are familiar with SBIRs, this is sort of something we want to get out in front of them. Hopefully that makes sense, because if you're listening and you know anything about small business, innovative research, what ends up happening is
I think we might have lost Brian. Brian, I think we might have lost some audio from you. Well, folks, if I can't get Brian back, who has
sort of,
oh, there we
yeah.
go. Okay.
Oh, did I cut out?
We need Brian to answer those questions. So Brian, if you can, I think where you kind of disappeared was as a R&D organization. So if you can finish your thought, that'd be great.
Yeah, just as an R&D, we're trying to get out ahead of this and market to whomever is familiar with SBIRs. Certainly, LIF is a big partner in getting another project off the ground into a so-called phase 3 posture. But yeah, hopefully there's going to be interest generated within this. That way we can really ramp it up and take it to more applications beyond the Air Force. Appreciate the question, though. It's a real good question.
Yes, and another question that came in, and I'm actually, not surprised. Obviously, with the Baltimore Bridge that took place, can this patch product be used as a full base for bridges, or is it really just patches at this point?
It could be used as a full base. You could form cast these patches, or these epoxy-based patches, into footers, structures. This would be absolutely right up the alley for the Baltimore Bridge. So the answer, the real quick answer is yes. This would do wonders. So
good to know. I think with this broadcast that that might help, and we'll get the word out, which is why we do these type of webinars and broadcasts, so we can inform the industry and the ecosystem and the defense industrial base. I have another question. Is this product commercially available?
No, it's not commercially available at this point. So we're at the tail end of a research and development. We have yet to find a customer that could take us over that proverbial finish line to make it a military or a purchase order specification. But no, we haven't turned it into a commercial product as of yet.
All right, I've got another question. What size of holes have been repaired during live demonstrations?
So the largest hole we fixed or patched was 8.5 foot by 8.5 feet. So pretty big hole. It started off, 6 inches deep, 4 inches deep, somewhere in there. My memory's a little, it's fading, but And then we've created small little pothole type filling applications. So real world, maybe 6-inch by 6-inch, 12-inch by 12-inch, 2 foot by 2 foot, 4 foot by 4 foot. All the food groups in between we've demonstrated, all have had really good success in all weather conditions.
Thank you for sharing that. Another question that came in, and I think you might have answered, it says, who's picking up the production? And I think you might have answered that, but.
So right now, for those in the know on SBIRs, we entered that phase 2 valley of death, and we're trying to get out of it, obviously. So no one has really picked up the ball in terms of the production. There's a lot of competitors out there with similar products, perhaps. Big prime contractors. That a small company trying to hurl itself into this space. We need help, and that's why we're doing this. So to answer the question, no one has really picked up the production part of it. We can do it. We just have to be, asked. For example, if Huntington Ingalls said, "Hey, come on down and fix part of our pier," we would do that, and to show, hey, this has merit.
Appreciate that. Another question, can you reprocess the material like asphalt?
That's a good question. We've never tried. My thought is that if we poured the patch and for some crazy reason they needed to crush it up, to be honest, I don't know. We would have to take a look at that, whether or not it could be reprocessed, having to, it would have to phase transfer or phase change. My knee-jerk reaction is to say yes, but it would be under certain circumstances where that could be possible or not. Sorry for the lame answer, but if somebody who's asking it could reach out to me directly, we could talk through scenarios where we could possibly do that.
I think that's a great segue. I think we've have a lot of technical experts, material experts that participate in these type of webinars and activities. So, and part of LIFT's mission is to really bring the ecosystem together to help accelerate and advance that technology, and this innovative technology, which is really critically important to the industry, to the communities we live in, if I could say that as well, but really important. So I have, that's all the questions that we have. We are happy to connect Brian to those that have specific questions and want to help accelerate this technology. Any other closing thoughts that you'd like to share, Brian, on this forever material that you shared with us today?
All I really want to say is to the folks out there, hey, thanks for taking time out of your day to listen to this. Obviously, we think it's a good technology. The bigger question is, do other people think it's a good technology? But we're in Westerville, Ohio. My POC. I think there's a white paper. I can send you a quad chart. Just thanks for giving me the time to talk about it and a lift. Thank you a lot.
You're welcome, Brian. And those documents that Brian referenced will be uploaded into this webinar and will be shareable. And thank you for joining us today for the Liftoff webinar, and have a great day, everybody.
Thanks a lot.